So welcome to today's class. So we will get started with a brief recap of where we were in the previous class. So if you recall, in the previous class, we were looking at this notion of controllability, wherein we were looking at if we had an equilibrium state, we wanted to essentially figure out whether, if we perturb or if we essentially drive the system away from the equilibrium state, can we design a control input U that would drive the state to the equilibrium state in finite time, right? So that is what our question was, right? So, and we say that a system is completely controllable if we are able to do that, right? So if we are given any arbitrary initial state and we essentially are able to drive that state to the origin, which is the equilibrium state in finite time, then we call the system to be completely controllable. And we essentially looked at a criteria for complete controllability by considering, so-called controllability matrix, which is essentially written in this form for MIMO and SISO system. So for constructing the controllability matrix, we need to look at the state matrix and either the input matrix or the input vector, okay, depending on whether we have a MIMO or a SISO system. For a MIMO system, the controllability matrix is given by B, A squared B, all the way till A power n minus 1 B. For a SISO system, it's given by the vector B and then A multiplied by B, A squared multiplied by B, all the way till A power n minus 1 multiplying. Okay, so and the necessary and sufficient condition for the system, right, to be completely controllable is the rank of this controllability matrix should be n. Okay, this is order of the system. So this is what we did. So let's start doing a few examples today. Like we will start working out some problems and then we will understand the concepts better. Okay, so once again, like throughout the discussion, I'm going to restrict by and large to second order systems. The reason is very simple, like because if you look at second order systems, at least the matrix calculations and the algebra is relatively simpler, so that like we can do things by hand and learn the concepts rather than focusing on the mathematics too much, right? So the complexity of the mathematics involved is also manageable. So that is why I'm essentially dealing with second order systems, but the concepts are applicable to an nth order system. Okay, so this is what we have. Okay, so let's say this is the state equation, right, of the system that we are studying. Okay, so immediately we can observe that this is a decoupled realization. Why do I call this as a decoupled realization? So if we recall from the previous class, whenever we have the state matrix to be a diagonal matrix, right, we have a decoupled realization, right? So if we write this state equation as two equations, we will get x1 dot to be equal to minus x1 t and x2 dot t to be equal to 2x2 t plus u of t, right? So that's why we call this as a decoupled realization. So I hope the meaning is once again clear. Okay? So essentially we are having a diagonal state matrix. Consequently, the evolution of any state, depends only on itself and the input potential. Okay, the evolution of a state does not depend on other states. Okay, so that is the concept. So once we are given this, we follow a similar set of steps that we looked at in the previous class. The first task is always to calculate the equilibrium state. How do we calculate the equilibrium state? We calculate Ax star to be equal to 0. So once again, of course, we don't even need to do these calculations, but I'm doing it once again. The fact that A is an invertible matrix will tell us that the origin is the only equilibrium state, right? But anyway, let's do this for the for understanding it once again in a better manner. So if we do the matrix vector multiplication, immediately we will get the solution for x1 star and x2 star as 0 and 0. So consequently, the state, the equilibrium state is the vector 0, 0, right? So yeah, that's it. Correct. So that's the equilibrium. So the next step is to calculate the eigenvalues of the state matrix. How do we calculate the eigenvalues? We solve determinant of A minus lambda I to be equal to 0. So once again, we can directly write it because we have a diagonal matrix, but I will do this calculation again incomplete, let's say completely, so that we understand. So if we do this, we are going to get determinant of -1 minus lambda 0, 0, and 2 minus lambda. Okay, and that will be equal to 0, right? So if we have this, we will have -1 minus lambda multiplying 2 minus lambda is equal to 0. So lambda is equal to -1 and uh, lambda equals 2, right? So the spectrum of A, right, or the eigenvalues of A will be are -1 and -2. So this immediately implies that the equilibrium state is unstable. Why? Because we have one eigenvalue of A in the right half of complex plane, right? So consequently, the equilibrium state is unstable, right? So that's something which we can readily conclude from this exercise. Okay. So next, what we do is that like we evaluate the controllability matrix. Okay. So in this case, please note that n is equal to 2. Okay. So this is a second order system. So n minus 1 will be 1. Right. So the controllability matrix will be only B and AB. Why did I stop at AB? Because if you look at the general controllability matrix for an nth order system, we go till a power n minus 1b, right? So when n is equal to 2, that is, we are dealing with a second order system, n minus 1 is going to be 1, right? So we are going to stop at a times b, right? So the controllability matrix will be b and a times b, that's it. Okay, so let's look at what happens. Okay, so what is b? B is going to be 0 and 1, right? What about a times b? Let's do that calculation on the side. Okay, so I'm just doing this calculation on the side. A times b is going to be equal to -1, 0, 0, 2, and b is going to be 0 and 1. So if we do the matrix vector multiplication, we are going to get 0 and 2, right? So I'm sure all of us agree with that. So this is going to be 0 and 2. Okay, so immediately we can observe that the rank of the controllability matrix is 1. Why do I say the rank of controllability matrix is 1? Because you can see that I can write this column as a multiple of the first column. Okay, so they are not what are called linearly independent columns. Okay, or the first row, I can essentially I can get the first row by multiplying the second row by 0 also, right? So essentially you can see that we don't have a complete set of linearly independent rows or columns. Okay, so as a result, the rank of the matrix is 1. Okay, the controllability matrix is 1. So that means that the realization is not completely controllable. Okay, so in this example, okay, so what we have is that like we have a system which is not completely controllable. Okay, what is the what do we then interpret from this, right? So that's important for us, right? So because we are interested in the what is that the physical impact, right, or the physical meaning, like behind this particular result, right, of the controllability matrix being not of full rank. Okay, so to understand that better, we are going to go back to the decoupled realization. All right, so we are going to also sort of interpret something interesting about decoupled realizations and when we have a diagonal state matrix. Okay, so let us go to the two-state equation. Okay, I'm just rewriting the two-state equation. So the first state equation is x1 dot is equal to minus x1. All right. So that is the first equation, and the second state equation is x2 dot is equal to 2x2t plus u of t. Right. So this is the second state equation. So now let's look at each state equation one by one. Okay? So if we look at the first state equation, we can immediately observe that x1t is going to be equal to x1 naught e power minus t. So this clearly shows that, you know, if we start with a non-zero initial state, you know, like as the initial condition for x1, we can immediately observe that the eigenvalue associated with x1 is -1. So we are going to get an e power minus t associated with that. So consequently, x power x1 of t tends to 0 as t tends to infinity. So this is a sort of like a stable state, but not controllable. Okay. So this state is not controllable because why? We are not able to influence it through an input, right, that we can provide, but it is stable, right? X1 consequently is not controllable, but it is stable, right? On the other hand, if you look at the second equation, right, let's look at this coefficient too, right? So this is going to get an exponential term e power 2t in the solution for x2. So in fact, we will see that this one, if we look at this particular equation, we will have a e power 2t term, right, in the solution for x2. And so consequently, what is going to happen is the following, right? x2 will blow off to infinity, right? So as t tends to infinity, and unless otherwise we take some corrective action. Okay, so by default, the evaluation of x2 is unstable, right? Why? Because we have an e power 2t term in the solution, right? And as we know, an exponential function with a positive exponent, right? That magnitude will blow off to infinity, right, as time t tends to infinity. So consequently, if we look at this, we can immediately conclude the following. We can conclude that the evolution of x2, although not stable to begin with, can be made stable, okay, by using an appropriate control input, u of t. Okay, so that is the conclusion. Okay, so consequently, this x2 is controllable. Okay, so whereas x1 is not, right? So if we want to summarize what we have discussed, we can immediately see that with this decoupled realization that we are considering as a simple example, our state x1 is stable, okay, but not controllable. What do we mean by not controllable? That is, we cannot have an input directly affecting the dynamics or the evolution of x1. All right, but the state x2 is unstable, okay, but controllable. Why am I saying controllable? Because we can immediately look at it from the equation that we can design a suitable input u of t to make the dynamics of the state x2 to be stable, right, when we design a closed loop system. So that is the point, right? So from this example, what we have learned are the following. That is, we have considered a very simple decoupled realization, right, where we had a diagonal matrix. We saw that the system to begin with is unstable, right, and we had two states. The first state was stable but not controllable. The second state was unstable but controllable, right? So this leads to a definition. So the we have a system, right, in which all uncontrollable states are stable. That system is called a stabilizable system. Okay? So let me write down the definition. Okay? A system in which all uncontrollable states are stable is called a stabilizable system. Okay, so that is an important definition. So what we mean is that, like, okay, see, even if you don't have complete controllability for designing a controller, if we can be assured that the states which are not controllable are stable on their own, right, inherently, then also we can design controllers and implement the closed loop system. Okay, absolutely, no issues. Okay, so in summary, the example that we have considered this time, right, is a system which is a stabilizable system, not a completely controllable system, but it is a stabilizable system. Okay, so that is the first example. Okay, all right. So I hope it's clear how we figure out whether the system is completely controllable and what is the notion of stabilizable and so on, right? From this. Okay, so now let's do another example wherein we have our state equation x star to be equal to -1, 3, 0, 2, x of t plus 0, 1, q of t. Okay, so once again, we can immediately observe that the value of n is 2. Okay, this is a second order system. And if you recall the previous example, in fact, the only change I have made between the two examples is that, like, we have replaced this entry, okay, which was previously 0 with 3. All right, so that is the main change that we have made. All right, so then we will see what difference happens. Okay, so due to this stage. Okay, so we can immediately see that we have essentially the state matrix to be a non-diagonal matrix. Okay, so it is no longer a diagonal matrix, and this realization is no longer a decoupled realization. Okay, so that's an important observation that we have to make, right? So because now we can observe that the off-diagonal element, right, in the first row is no longer 0, right? We have replaced it by 3. All right, so that is what we have done. Okay, so once we have done that, okay, so we first follow the same set of steps. We essentially solve for the equilibrium state. Once again, it's always better to calculate this and get the equilibrium state, but as we already should have figured out, the equilibrium state is origin. Why? Because the matrix A is invertible. But however, I will do the steps completely. All right. So in fact, if we do the matrix multiplication, we get -x1 star plus 3x2 star is equal to 0. That's one equation, and then we get 2x2 star equals 0, right, by multiplying the second part. So from this, we get x2 star equal to 0. And then using these two equations, we can immediately find out that x1 star is also equal to 0. Right? This implies that the equilibrium state x star is going to be 0 and okay, so that's what we can immediately figure out. Okay, so that is the first step. So how about the eigenvalues? In fact, the eigenvalues are the same, but anyway, let's do this step because what happens is that this is what is called as an upper triangular matrix, right? So we can immediately see that the lower the term in the so-called 2-1 position, right, is 0, right? So the subdiagonal term is 0. So essentially, this is an upper triangular matrix. So even for an upper triangular matrix, the eigenvalues are going to be the diagonal elements. But however, we'll just corroborate it. Okay, so we can essentially calculate this. So we are essentially going to have determinant of -1 minus lambda, 3, 0, 2 minus lambda, right? That is equal to 0. So if we calculate it, we are going to get -1 minus lambda times 2 minus lambda is equal to 0. So this will get to us lambda equals -1 and 2. Okay, so we can observe that we are going to have the same set of set of eigenvalues. So this means that the equilibrium state is unstable. Okay, so that remains. Okay, so now if the equilibrium state is unstable, what about controllability? So let's calculate the controllability matrix. The controllability matrix is going to be B and AB, right? Why? Because once again, n is 2, so n minus 1 is 1. So we go only till B and AB. So B is going to be 0, 1. What about AB? Okay, so let's evaluate A times B. If you multiply the matrix A, which is -1, 3, 0, 2, the vector 0, 1, we are essentially going to get the answer as 3 and 2. Right? Okay, so that's what we are doing. So immediately we will have the second column as 3 and 2. So from this, we can figure out that the rank of the controllability matrix is going to be equal to 2. Why? Because you look at the two columns or the two rows, right? We cannot express the one row as a multiple of the other, right? So I can't express 3 by 2 as some multiple of 0, 1. Similarly, I can't express 0, 1 as a multiple of 3 and 2, right? So we can see that these are what are called linearly independent columns. So similarly, if you look at the rows 0, 3 and 1 and 2, right? The two rows are also linearly independent, okay? So that's why the rank is 2 here for the controllability matrix. So consequently, the system is completely controllable. So now this result is very interesting, right? So what has happened? We just replace that so-called super diagonal element 0 with a non-zero value, right? And things change in what completely. Why did things change? Okay, so let me write down things now, right? So if we write down the two state equations now, x1 is going to be equal to minus x1 plus 3x2t, right? That's going to be the first state equation. How did I get this? From the state equation that we are given, right? So we just multiply the state matrix with the state vector, and then we will be getting this, right? And similarly, if you go to the second state equation, what we will have is the following. We will have x2 dot t is equal to 2x2t plus ut. Okay, so in fact, we can observe that u of t comes explicitly in the second state, right? So essentially what we can observe once again that the second state can be regulated by the input u, But how come the result suddenly changed to complete controllability? That means the first state is also can be regulated by the input. How did it change? That is because of this term. Okay. So, although we don't see u of t explicitly in the dynamics of x1, we can immediately observe that the dynamics of x1 is going to be influenced by the evolution of x2. And since the evolution of x2 can be influenced by u, in a sense, the control input can also be used to regulate the evolution of x1. So I hope now it is clear why we had complete controllability, right, in this particular case. Whereas in the previous case, when we had a decoupled realization, we did not have u of t or x of t, right? In the x2 of t, the evolution equation of x1 t, we did not have complete control. Okay? So I hope the subtle difference is clear, right? So I wanted to do the simple example just to convey that, how, to interpret controllability, right? Using the equation and also the physics. Okay? So we can immediately see that we don't need the input to explicitly appear in the state equation of each state. However, if we have a coupled realization, like what happened in the second problem, this is a coupled realization, right? Why? Because you can see that the evolution of x1 is dependent on x2, right? So, and since x2 can be controlled by u, x1 is also controlled by u in an indirect way, right, through x2. Okay? So that is why the system has become completely controlled. All right. So that is the result. Right. Okay. So I hope these two examples are clear, right? So once again, when we are given any system, what we need to do is the following. Like we need to essentially find the equilibrium state. Find the eigenvalues of the state matrix to comment on the stability of the equilibrium state, and then calculate the controllability matrix and evaluate the rank to figure out whether the given system is completely controllable or not. Okay, so these are the 3 steps to follow. Okay, till now. Okay, so we will see how to use it, use these steps in controller design subsequently. Okay, so now what I'm going to do next is to talk about what is called as a controller canonical form. So if you recall, at the beginning of the discussion on state space realization, right, I mentioned that as we go forward, we will learn some canonical forms, right, because given any system, we should be in a position to figure out how to write the state space realization of the system, right? And I mentioned that there are some standard forms which are called canonical forms, which aid us in doing it. So let's look at the controller canonical form. So I'm going to do it for n equals 3 and 2, okay, rather than for the general version. So let us consider, I'm just going to write the result, okay, once again. So and we will see how it is useful, okay. So I think after today's class, like when we have all the blocks in place, we will see how to put together all this theory in our control design form. Okay, yeah. So let's learn the controller canonical form. So let us say we have a third order system whose governing equation is given by y triple dot t plus a1 y double dot t plus a2 y dot t plus a3 y of t. That is equal to b1 u dot t plus b2 u dot, b1 u double dot t plus b2 u dot t plus b3 u of t. Okay, so that is the governing, let's say the general governing equation for this third order system. Okay, so once again, please note that I'm going to write the controller canonical form not for an nth order system. We could do it, but just to keep discussion simple, I'm going to write down the controller canonical form only for n equals 3 and n equals 2. Okay, so immediately we can figure out that the Planck transfer function is going to be y of s by u of s is going to be equal to b1 s square plus B2S plus B3. That's going to be equal to S cube plus A1S square plus A2S plus A2. Okay, so this is the this is the plant transfer function. So I'm sure all of us know how to do this by now, right? So we take the Laplace transform and then we essentially apply zero initial conditions, cross multiply, and we get the plant transfer function of this resource system. Now, if we want to write down the state space representation in the controller canonical form, this is the controller canonical form. Let me write it down, then we will figure out what to do. Alright? And we will also learn what is the advantage of this form. Okay, so please note that this is a third order system. So we have three state variables. So x1, x2, and x3. Okay, so we need to write the state equation in this form. Okay, and the output equation y of t should be some c as the output vector dotted with x1, x2, x3. Okay, so this is our output equation. Now, how do I fill up these matrices and vectors? Okay, so what we need to do is that, like for the state matrix, first what we do is that the first row is always 0, 1, 0, and the second row is 0, 0, 1. So you can see that the so-called first super diagonal, okay, is filled with 1. And the last row is filled with the coefficient in the denominator of the transfer function from the left, from the right, but with the minus sign. So we start with the constant term, which is A3, but we write minus A3. Then we write minus A2 and minus A1. Okay, so that's how we fill the last row, okay, of this particular state matrix. Okay, so once again, let me repeat. When we want to write the state matrix, till the last row, what we do is like we fill the first super diagonal element of each row with 1. Okay, all the other elements are 0. Okay, and then like the last row, we look at the coefficient of y dot, and y double dot, and we multiply it by the negative sign, and then we write them. Write the last word minus A2, minus A2, minus A1. Okay, so that's what we do. And the input vector we just write as 0, 0, 1. Okay, that's it. Okay, so it doesn't matter what is the order of the system. Okay, so we fill it with 0, and the final element is 1. Okay, in the input vector. All right. Then if we go to the output equation, what we do is that like we once again look at the right hand side or the numerator polynomial. Once again, we come from the constant term, which is B3, and then the coefficient of S, which is B2, and the coefficient of S squared, which is B1. We write it in this order, but then like now we don't multiply by a minus sign. Okay, so it's all going to be a positive sign. Okay, so that's the difference. Okay, so this is the controller canonical form. So the controller canonical form essentially is written in this way. So once again, I have written for n equals 3. All right. So please note that I have written for a specific case where n equal to 3. So we have 3 states, and we have to write the controller canonical form in this manner. Right. Okay. Fine. So let me write it for n equals 2 also. So once again, as I mentioned, like I am writing for very specific cases. Okay, so let's consider n equals 2, wherein we will have the governing ODE to be y double dot t plus a1 y dot t plus a2 y of t. Okay, that's going to be equal to b1 u dot of t plus b2 u of t. Okay. Please note that this is a second order system. Okay, and what is the plant transfer function here? So if we evaluate y of s by u of s, we are going to get b1 of s plus b2 divided by s square plus a1 s plus a2. Okay, so that's what we have. All right. So as our plant transfer function. So now we essentially will have two states, right? So because this is a second order system, so we have two states. So let's write down the state equation. So x1 dot and x2 dot. All right. So that's going to be equal to uh, state matrix multiplying x1 x2, right? Then the input vector multiplying u of t, and the output equation is y of t, which is the output vector dot product with the state vector, right? x1t and 2. Okay, so this is what we have. All right. So now we go and fill. Okay. So once again, how do we do this? If you look at the state matrix, we will put 0 and 1 as the first row. Okay. And then what we do, we start from the right. Okay. As far as the coefficient of y is concerned, but with the negative sign. So we write minus a2 and then we write minus a1. All right. So that's it. Okay. So that's how we write the second row of the state matrix. Okay, and the input vector will be 0, but the last element will be 1. In this case, the last element is the second element, so we have 0 on that. Okay, what about the output vector? Once again, we start with the coefficient of u, and then we write the coefficient of u. Okay, so we write b2 and b1. Right, so this is all. We write the controller canonical form for a second order system. Fine. So we will see what is the advantage of this controller canonical form when we do the controller design. There is a specific reason why I am discussing this. But however, let's apply it for an example and then see what we have, right? So the well-known mass spring damper system, right? For which n is equal to 2, right? And we already know that the plant transfer function is 1 by ms square plus cs plus k. All right. So now the task is to essentially write this in the controller canonical form, right? But before we write in the controller canonical form, we need to ensure that the coefficient of the highest derivative of the output term is 1, right? If you look at the right-hand side of the governing equation, y double dot has a coefficient of 1, right? So, but here we have m as the coefficient, right? So what we need to do, let's divide both sides by m. Okay, so what we do is that we divide both sides by m, then we have x double dot t plus c by m x dot of t plus k by m x of t to be equal to 1 by m f of t. Okay, so please note that this is a system. This mass spring damper is a dynamic system to which we provide force f of t as the input and we get the displacement x of t as the output. Okay, so that's what we have. All right. Okay. So now, if we compare it, now we have it to the standard form, right? Let's compare. Okay. So what are we going to have? A1 will be C by M. Okay. A2 will be equal to K by M. Okay. We just compare. B1 is 0 because there is no derivative of the input term. And B2 is 1 by M. That's it. We are done now, right? So we can immediately write the controller canonical form, right? Is it not? So the controller canonical form is going to be equal to the following. X dot equals, this is a second order system. So we are going to get this as so the first row, the state matrix is going to be 0, 1, minus k by m, minus c by m. All right. And the output will be equal to 1 by m, 0, dotted with x1 and x2. So this is another realization for the same mass spring damper system, right? You can see that this is the controller canonical form for the mass spring damper system, right? So I hope this is clear. Okay. So if, in fact, if we look at this new realization, we write the matrix A, the input vector 0, 1, the output vector in this case is 1 by m0, and the direct transmission term is 0. So if you recall previously, when we initially learned the state space representation, so we got the state matrix to be the same. However, the input vector was 0 and 1 by m, and the output vector was 1 and 0, right? The direct transmission term was 0. Okay, so you can immediately see that we have written two realizations of the same system, right? So this is the controller canonical form that we learned today. Okay, that is this, and we essentially had this realization previously. Okay, so I'm going to leave this as an exercise to you to think about. Please find out what is the relationship between these two realizations, right? The state matrix looks to be the same, but then the output input vector and the output vector are slightly changed, right? So you can essentially think through, right, and then get back to me in the next class. Okay, but also another exercise that I will leave it to you is to calculate P of S using this controller canonical form. Okay, so calculate the plant transfer function using this realization. Okay, and just double check that we get the same plant transfer function, right? So that will also sort of corroborate our earlier statement that the plant transfer function is unique for a given system. However, there can be multiple infinite number of state space theories. Okay, so that is the that's an important. Okay, so that is the controller canonical. Okay, so any questions on the concepts learned today? So today we have done a couple of examples to get a feel of controllability, and then we have learned about the controller canonical form. In the next class, we are going to put all these things together and learn how to design a controller based on the state space theory. Any questions? Okay, so if not, let me stop recording today's session, and we will continue in the next class. Thank you.